So in this case, if you first of all determine the strain profile of this section, the strain profile, if the neutral axis is located within the section, then the section would go into tension as well as compression. Now, if the neutral axis is located outside the section, then the whole section would be in compression. Now, let me define that. If this is what is given to you, what is given here is if xu is equal to 1.2, then xu by d is equal to 1.2. That would mean that the neutral axis is greater than the depth of the section, greater than the depth, this d, not small d, this is capital D as given in the question. Then it would be somewhere here. Where would the neutral axis be? It would be somewhere outside here. Now, if I don't assume for the time being, मैं अभी assume नहीं करता हूँ what is given in the question. If I just begin to calculate from here the neutral axis for this section, then in that case,
सर इसमें जो हमने ये सेंटर टू सेंटर डिस्टेंस निकाली, इसमें हमने 600 में से दोनों साइड से कवर का मल्टीप्लाई करना था ना सर, फिर डिवाइडेड बाय 2।
दोनों साइड से
नहीं,
एक ही साइड से किया। 600 minus 40 minus 40 minus 8 minus 8 minus then 20, right? So that would be 80, 80, 16 plus 20, that's 116, 116. So this is 242. Sorry, this is 242. This is also 242 then. On the edge, this is right. 58, 58 is right. So how would the strain profile look like here? Now your strain profile would, if the neutral axis is within the section, the strain profile would look like this. If I'm assuming that there is a xu, there is a point xu which is shifted away, somewhat like this, shifted away from the center where the neutral axis is located, then this point would be the neutral axis point. If the neutral axis is shifted away from the center. So this is what you mean by eccentricity. First of all, this is how you get the eccentricity. Eccentricity is the distance here from the center of this. Now from this point up till this point would be your eccentricity for this column section. Now half of the column here is in compression and the other half is then also becoming under eccentric loads, it's coming under tension. So this portion is then under compression and the other portion then comes under tension. Although both the portions are vertically, actually they are in compression, but when you are determining eccentric loads, so for moments, now moments are acting here. The moment is acting like this. This is the moment. Rather, its direction would be, yes, this would be the direction. M x, about x direction. If this is the x direction, if this is the x direction, then there would be moments mx, which would be developed by the eccentricity ex. Then you would have the other portion coming under tension. Now let me check for this. There is a steel bar here and correspondingly another steel bar here. Then there is also steel bar here. So for this portion, right here and right here, you have steel bars. Now they are also contributing in compression and tension. The strain, this is a strain profile. For a eccentrically loaded column, strain at when the neutral axis is within the section. I'm right now not assuming that xu by d is on 1.2. I'm assuming the neutral axis is somewhere within the section. I'll be calculating the neutral axis and its eccentricity manually without assumption. Eccentricity here is ex, and your this e cu, which is the extreme fiber within compression. Now, do you understand how this portion came in tension and this portion in tension? What is happening is that the column would be somewhat like this along the elevation. Along the elevation, the column is like this. You have a load acting on the column somewhere here. While as the center of the column is somewhere here, then in that case, this portion bends like this, so it comes under compression, and this portion comes under tension. That's why this portion is in tension and this portion is in compression about this neutral axis. Now, the extreme fiber here, ECU, is in compression. Now, what would be the amount of compression in the extreme fiber when you have flexural loading now here? Because you are treating it as flexural loading, not the crushing load. It would be 0.0035. The amount of maximum amount of, this is maximum amount of compression strain, maximum strain at the extreme fiber within compression is 0.0035. Similarly, you would have these steel bars, this one EY1, this is the first steel bar. Yes, we have more steel bars here, these ones. So this portion is also under tension load. So you have steel bar under strain EY2. This was EY1. Then you have steel bars under strain EY2. Then you have steel bars here under compression EY3. And then you would have, if now I wanted to check what is this now, right from here, this point up till this point, This is XU. It's the depth of the neutral axis. It's somewhat like you are now treating it as a beam. आप अगर इसको reverse करोगे, you can treat it as a beam once it's in the eccentric load, because then half of the portion is coming under. Now this is the depth of the neutral axis, and the lower portion of this, if you treat it as a beam, would then be under the tension. Now this is, it's like a beam with EY3 here being the under compression, and EY2 and EY1 steel bars being under tension. Now, like in beam, we assume that there is no amount of tension taken by the concrete. So, the stress envelope would be somewhat like this. So this would be the stress envelope. Now, again, like in beam, this would be 0.447 FCK, and the other portions would be the, like in beam, you would have the center of the compression. If this is the compression, which is C, and here we can treat it as C1, because you have many more C here. You have the other C provided by the the steel bars at F3 location. So this is C1. Now why does C1 act? It acts at 0.416 XU, as we have already calculated in the flexural, when we were checking the flexural there. If you remember, it was D minus 0.416 XU, the moment equation. So then you also have C acting right here below this. The other C would be acting absolutely under this point. So there is C acting here, which is C2. Now C2 is acting due to the, then C2 is acting, and the C2 is the compression force taken by the steel bars. Then you have the tensile forces taken by, number one, by this steel bar right through the center. It will go through right through the center of this. So that would be the load taken by the steel. This could be TS2, and this would be TS1 below this one, below EY1, it would be TS1. So no tension forces. This is the stress envelope, is assumed to be taken by the steel and the concrete. Now this would happen when you have a balanced condition, and where we assume like in that the section is balanced such that your xu by d is equal to xu max by d. Now this would happen in that case. So if we check the from this, if we now determine the first of all, what we'll do, we'll determine these strain profiles ey, e1, ey2 and ey3. Now if ecu is at point 0035, can you determine ey1, ey2 and ey3? Yes, we can determine that. Now this is your compression envelope. Here it's ECU is 0.0035. Then you have EY1 here, EY3 here, or epsilon 3, epsilon EY3, and you have XU. This is XU. Now, in order to determine that, for first of all, what for Fe500 steel, what would be EY? What would be the value for Fe500 steel? What is EY? Can you tell me how to determine that? Yes, any one of you? Point 002 plus 0.87 Fy divided by Es is the strain in steel. That is 0.87 into 500 divided by 2 into 10 raised power 5. That is so this is 0.002 plus 0.87 into 500 divided by 0.004 is the strain in the steel. Now then in that case XU B